Okay, I'll wait. Should I wait for 30 seconds? Okay, good afternoon, everyone. So today I'll talk about the RT-Xen, real-time virtualization. I'm Sisu from Washington University in St. Louis. I'll cover the first part, and also Meng Xu from UPenn will cover the second part. Without further ado, let's get started. So we see more and more applications real-time applications are being deployed in a virtualized environment. Take the cars, for example. Previously, there's around 100 ECUs, and right now there's a trend of consolidate those applications on just tens of multi-core processors. For example, the infotainment system on Linux and Android, and also the safety critical control on the AutoSAR standard. Not only the embedded systems, we see the real-time applications are being deployed in a virtualized environment. It's also the trend in the cloud computing. For example, one IEEE Spectrum article says, the cloud computing's killer application is gaming. And in that article, it says, it needs to compute and stream 30 to 50 frames per second to the end user. These applications must meet their real-time performance constraints in a virtualized platform. Okay. So here is what we did. We did the RT-Xen, which is a real-time hypervisor scheduling framework in Xen. We implement a suite of real-time scheduling algorithms, and it is based on the compositional scheduling theory, which provides the theoretical guarantees. Each virtual machine would specify its resource interface, and based on those resource interfaces, we can guarantee the real-time performance to the tasks running in a virtual machine. I'll talk about the interface in the next slide. It is open source, and we already submitted the RT-Xen patch to the mailing list. And this is the RT-Xen website. So I know all of you are familiar with the Xen architectures, but let me just spend less than 1 minute on this slide. So this slide shows the Xen scheduling architecture. Basically, the guest OS runs on a set of vCPUs, and the hypervisor or the Xen scheduler schedules those vCPU on a set of pCPUs, physical CPU. By default, Xen provides a credit scheduler. The resource interface has two parameters, the weight and cap per virtual machine. Weight represents the relative resource share you will get, and the cap is the upper bound limitation for it. And underneath it, it's a round-robin scheduling scheme, which means A, B, C, and then go back to A, B, C. You take turns. In RT-Xen, we changed the interface like this. Each virtual machine still has a set of vCPUs, and each vCPU is characterized by two parameters, period and budget. We also support the CPU mask, so you can specify the CPU mask to ping a vCPU to a specific core. Sorry. And in this way, we would hide the task-specific informations. So based on this interface, we need to design the real-time schedulers in RT-Xen. There are three choices we have. The first one is the ordering of the vCPUs. This relates to the priority schemes in real-time area. The second is how do we place those vCPUs? In real-time area, that's the global scheduling versus partition scheduling. The third option is how do we achieve the resource isolation? It is a server mechanism in the real-time area. I will explain these three parts in detail next. Okay, first, let's look at the priority schemes. We know that each vCPU has a period and a budget. So there are two priority schemes we consider. The first one is static priority scheme. Here we consider the deadline monotonic. Basically, the shorter the period, the higher the priority you have. The second one we consider is a dynamic priority. Here we consider the earliest deadline first, which is basically the earlier the deadline, the higher the priority. We assume the deadline equals to the current period. When it comes to the global scheduling versus partition scheduling, in global scheduling, the vCPU scheduler schedules vCPU based on global information. It allows vCPU to migrate across different cores as long as it's subject to the CPU mask constraint. The benefit of global scheduling is it has the benefit use or flexible use of underlying multiple pCPUs. However, when you migrate a vCPU, you might have some overhead and also some cache penalty. In contrast, A partition scheduling would assign and bind the vCPU to a specific pCPU. And each pCPU schedules those vCPU based on its local information. You may face the bin packing problem, so you may underutilize the underlying pCPUs. However, there's no migration overhead or the associated cache penalty. A third thing we consider is a server mechanism. We actually consider a lot of real-time scheduling servers. Here I give one example of the developer server here. So a vCPU would receive budget microsecond of CPU resources every period microsecond. And the budget is replenished or reset at every start of the period. Whenever a vCPU is running, it consumes its budget, and it would suspend when it runs out of budget. Different server differs in how they deal with a case when you still have budget and you are the highest priority, but you have no task to run. In this example, the developer server here, the upper part shows there are 2 real-time tasks, while the lower graph shows the developer server budget consumption. The x-axis is the time, and you can see from time 0 to time 2, when this server is the highest priority but have no task, it would preserve its budget until the task arrives and then starts consuming it and running. This is work conserving because in this time period, a lower priority server can occupy the CPU resources. Okay, this kind of shows our investigation roadmap. In this graph, the x-axis represents the global partitioning, global scheduling versus partition scheduling. The y-axis represents the fixed priority versus dynamic priority. And we draw different server schemes in the square here. We actually have 3 versions of RT-Xen, and our patch is based on the global EDF plus the developer server here. So let's get to the implementation detail. Here is how we design the run queue. Run queue is the most important data structure in a VMM scheduler. It hosts the vCPU that are runnable or has tasks to run. In RT-Xen, currently we divide the run queue into 2 parts: vCPU with budget left and the vCPU that runs out of budget. Within each part, the run queue is sorted by the priority. It can be deadline monotonic, or it can be the earliest deadline first. We provide 2 implementations. One is RT Global, in which case all the physical cores would share one run queue protected by a spin lock. The other one is a RT Partition, in which case each pCPU has a dedicated run queue, and it schedules based on its local information. Patches for more efficient implementation is on its way. Okay, let's look at some experimental results. Here is a setup. So we have an Intel i7 processor with 6 cores. We disable the hyperthreading and also the speed step, so it runs constantly at this speed. We dedicate one pCPU to domain 0 and run all the guest VMs using the remaining 5 cores. This is a cache architecture. We also have results for the cache-intensive workload, but due to time constraint, it's not shown in this presentation. For the software, in the experiment, we use Xen 4.3 patched with RT-Xen. And for the guest OS, we use Linux patched with Litmus RT. Litmus RT basically provides the global EDF scheduler in the Linux. First, let's look at some overhead measurements. I measure the overhead spent in the due schedule function, and this is the result. This is a SEDF plot. The x-axis shows the overhead in nanosecond, and the y-axis shows the fraction of events. I measure it for the RT Global, RT Partition, and the credit scheduler. I cut the x-axis at 3,000 nanosecond and show the 99 percentile and the max value in the legend here. The first thing we'll notice is RT Global compared to the RT Partition, it has some extra overhead. We attribute this to the global spin lock. Okay. The second thing we notice is credit scheduler actually has this high maximum overhead. We attribute that to the load balancing scheme in the credit scheduler, because it's basically a partition scheduler with load balancing. After that, we also run some real-time tasks. And here is the results. The x-axis represents the task set utilization. Remember, we have 5 physical cores to run the real-time task. So the x-axis ranges from 1.1 to 4.9. This represents the total task utilization. Every data point here represents 25 randomly generated task set. And the y-axis shows the fraction of schedulable task sets among those 25 task sets. We can see that by using the credit scheduler, because it's round robin, it has no priority in it. It starts missing deadline at merely 22% of the CPU capacity. In sharp contrast, if you use RT-Xen, we can deliver the real-time performance guarantee up to 78%. Finally, we also do the constructed experiment to compile the global scheduling versus partition scheduling and different server schemes. This graph clearly shows that the global scheduling wins empirically, so the SEDF plus the deferrable server delivers the best real-time performance. Our RT-Xen patch is also based on the SEDF plus the deferrable server. Okay, I think next, Ben will come and show the demo.
Thanks. I will give you a quick demo of how the RT-Xen, the real-time scheduler patch, the user face of the real-time scheduler patch. This is the, basically this is the configuration we are using for this demo. We have a machine with 4 cores and install the Ubuntu 40.04 as the domain 0, apply the patch to the latest Xen 4.5 versions of code. After we boot it up, we created 3 guest domains. Each guest domain has 2 vCPUs. Right now, we are creating these 3 guest domains. Okay, first we check that we are running with the real-time scheduler on this Xen 4.5 unstable version. This is the domain 0's Linux kernel, which is the 3.13. Okay, so this is the setup we use for this demo. Now I'm going to show 2 important user operations for this real-time scheduler. Basically, it's getting and citing the information of each vCPU over domain. The difference with the credit scheduler is that we need to specify each vCPU's parameters for a real-time domain instead of specify the parameters for a whole domain, which is used in credit scheduler. As you can see here, the vCPU column specifies the unit index of the vCPUs for this domain. And the second thing is the period and budget are in the microsecond instead of millisecond. This is because for the real-time application, people usually specify their requirement in terms of microsecond instead of the millisecond used for the credit or credit 2 scheduler. Okay. We can also cite each vCPU's parameters by specifying this domain's name, vCPU index, and the new period and budget. Here we are citing the 2 vCPUs of this VM1 to be a full capacity vCPU, which means its period equal to its budget. This is important. We need to treat each vCPU differently because these parameters of each vCPU will affect the scheduling sequence and then affect the guest domain's real-time performance. Of course, you can also show the parameters of a specific domain. I think this is very simple. This is the first part. These are 2 important user interface for this real-time scheduler. Actually, the rest of this demo video shows our real-time scheduler works with the CPU pool because of the time constraints. I will just skip here. Basically, what we did here is we remove 2 cores from the default pool 0 and create a CPU pool with credit scheduler and migrate 1 VM to the newly created CPU pool. we uploaded the video to the YouTube, so if you search RT-Xen demonstration, you can watch the rest of the video. Okay, so here is the patch status. We have already posted the first versions of the patch. As the after the version 2, actually this real-time scheduler can work very well on at least on our machines. It uses the global EDF scheduling policy with the deferrable server mechanism. We are going to release the third version of the patch, which will add the trace support and also try to improve the performance by avoiding scanning the whole queue when we insert a vCPU. And for the version 4, actually it still focuses on the performance improvement. It has two parts. One is we want to use the timer to replenish a vCPU budget instead of checking if we need to replenish a vCPU budget every millisecond. And second thing is we want to improve the timing resolution of the budget. Right now, when we burn the budget, we burn it in every millisecond. But if a vCPU has less than 1 millisecond budget, we still let it run for 1 millisecond. So it may overrun less than 1 millisecond for every period, which we think we can improve it to make it more precise. But if actually when the budget is large, this doesn't affect much. Okay, to conclude, actually our RT-Xen project implemented and evaluated various real-time scheduling policies, as Sisu just showed us, and compared our real-time scheduling policies with the credit scheduling policy. We just extract the best one, which is the global EDF with deferrable server, to try to upstream it. We also have another parallel project, which is called the compositional scheduling analysis to compute the parameters for each vCPU of each real-time domain. Based on the domain's workload, so that when this domain is configured like this, the workload inside this domain can guarantee its real-time performance. And this is a historical view of our project. We have been working on this for 5 years. These 3 papers, okay, we start with the real-time scheduling policy in Xen on uniprocessor and then move to the multiprocessor scheduling policies. And these 3 papers actually did the comprehensive evaluations and measurement. So if you are interested in the more data, you can have a quick look at that. We also have the real-time OpenStack and real-time inter-domain communication because it's not related to the real-time scheduler part, so we didn't talk it in this presentation. So that's it.
Is there a reason you did you test any of this with the Credit 2 scheduler?
No.
Okay.
Because credit 2 don't support the cap. I think we tested the credit with the cap and without cap. The result showing here is without cap.
Okay. Okay. So, but the Credit 2 scheduler was designed more for latency sensitive kind of workloads. So I'd be interested to see how that changed.
I think the latency sensitive workload you're talking about is the wake up function. That's the I/O workload. Here, the evaluation results shown here are all CPU intensive workload. Does that make sense to you?
Okay. Yeah.
When you're talking about real time, are you talking about hard real time or soft real time?
Soft real.
That's what I thought. Just checking.
You guys quantified all the other like Xen events that are going to take some appreciable amount of time. You talked about how much scheduling time it takes. It's 1,000 milliseconds per scheduler, but you're talking especially hard real time, more hard real time stuff. You need to know every non-deterministic aspect of the system, right? So, have you guys looked at that at all? Or?
So you mean to make other aspects to be more deterministic?
Yeah, I mean, I don't have a good example off the top of my head, but just wondering if there's other areas beyond just,
Scheduling. Yeah, actually, what I'm looking at right now is the shared cache effect on other domains. For example, I did a simple experiment show that even you pin the vCPU on a physical core and running 2 domains separately. So basically, they don't have the CPU interference. But if I use a simple task, just load all of the cache, put all of the L3 cache, it will affect other domains' workloads a lot, especially if another domain is doing some memory-intensive task. It just will make the performance, I think, at least twice worse. Yeah.
And also, we looked at the network I/O.
Maybe it's just nice to have like the kind of like worst case, balance on a lot of that. Just when people are designing, it's not just at least have the worst case.
Right.
When you mix, real time, what is it? You need, but the real time guess and non-real time, okay, and run them. What happens? For example, what happens to the non-real time?
I can answer this one. So in this slide, in the current version, the non-real-time virtual machine uses the same interface as a real-time virtual machine. We schedule them together. We treat it as a real-time virtual machine. But we do have work to add another parameter to the domain to say whether this is a real-time domain or non-real-time domain. And then that the real-time domain has strict higher priority than the non-real-time domain. But it's not shown here.
Basically, the non-real-time domain will consume all the CPU cycles left out by the real-time domains.
So if real-time guys spend a lot of them, then non-real-time customers are around.
Yeah, we don't, because you are running some real time, so we assume it has higher criticality. So yeah, if it has more workload, you should not let the background task run, right?
Well, that's one of the functionality that RT-OpenStack that we provide. It has this mapping algorithm that cleverly maps the vCPU to pCPU so that the real-time CPU, the real-time VM will not overload any individual pCPUs.
Do you have an example workload that you use to test difference? Because I'm not that familiar with real. So which one would be a CPU-bound real-time task that one could run as a test?
The results we obtain here are just a synthetic workload. So basically, each task is periodically triggered. It takes some time to finish, and it's all CPU intensive. And for the real application, we're actually looking at it right now, trying to emulate a gaming server, so it can periodically process a brand new.
So so a gaming server would be an example.
Yes.
Okay.
Like the first slide
Video
shows.
encoding comes to mind.
Yeah.
Especially trying to keep correlation between video and audio.
So your workloads are they burn CPU for a while and then they go to sleep.
Yes.
And they wake up again. Okay.
Yes.
Well, that's exactly what the Credit 2 server was actually designed to work well for. So I think you should test that one and see how it fares compared to.
Yeah, sure.
Yeah.
Is it guaranteed with certain time
So there's no guarantees, but it's specifically if what your VM does is it wakes up for a short period of time and goes back to sleep again, then we'll sort of end up sort of.
Oh.
better than that?
So yeah, so Credit 2, sorry, Credit 1, for any kind of latency sensitive, anything like that, was really awful, right? I mean, so in a way, it's almost not, it's like picking on,
Fair enough.
it's not really comparable. So yeah, if there was no Credit 1, then, if there was no Credit 2, this would be a fair graph, because Credit 1 is actually really awful for lots of, any kind of latency sensitive application, particularly audio, but also things like TCP, where work that I do now creates work later. Credit 1 is really, really bad for that. Credit 2, I designed it for audio, for network stuff like that. And it doesn't have any guarantees, but it does a better job of making things very graceful. And if there is enough CPU for you to do your work, usually you actually end up being able to do it. That was at least in the workloads that I was playing with. So.
about it.
I already did that. The RT OpenStack, I installed OpenStack with the Xen server, but it's not because of the Xen server 6.2. So then it's based on 4.1.
Yeah, we do support GPU on Xen services too. I have it.
So is the plan for 4.5 that should be like you option out which schedule you want to switch to?
Well, we've already got, so actually there's already 3 schedules. There's already 4 schedules in Xen. You can switch them out. So this is why so credit 2 is already in. It's sort of, it's more experimental because I worked on it a couple years ago and I haven't had time to go back to it. And then there's another EDF scheduler which is like ancient and completely broken. And this one or maybe another one, there's a couple competing ones that this was going to replace. And then there's a custom one that's for very specific tasks. But having an extra scheduler, if it's all kind of walled off from the rest of the system, it's just an extra file in there, so it doesn't matter. So
So there was this question about the SEDF scheduler. How does this connect to this?
this was going to this one and or there was a competing one, but there was it was going to replace this set of schedules.
Okay.
So this kind of schedule is kind of broken right now, and we're hoping to replace it.
Oh, okay.
And this is one of the candidates to replace it.
Okay.
It's like RT-Xen is this one, global EDF, with different server. The existing SEDF is partition EDF with some undefined server.
It's also not SMP and all sorts of shortcomings like that.
Yeah.
I think that was 2 years or more than that, but Samsung had signal sync. Did you take a look at
Which kind of?
real-time Xen?
We know one person in Korea did something on the ARM platform. He's using the credit scheduler and measures to try to improve the latency. We know that work very well.
Then they were doing more complex things, but some of math and then not like a deadline scheduler. But,
Yeah, they did lots of changes to the hypervisor itself.
Yeah.
Upstream.
Yeah.
Key difference.
Yeah, I think we are doing 2 different things, maybe. Yeah, and at that time, maybe we don't have them on ARM, right?
So they did change to their own separate code base. So they never went upstream. Some of the ideas might be reusable, so maybe even some of the code. But you would have to go and pick it up from Tarbos.
In the interest of time, let's